function that we want. And this generalized derivative formula, let's see if maybe we can make sense out of this in terms of the definition we already had. When in doubt, as far as the chain rule is concerned, you can go back to the definition. If y is a function of x, and you can have an intermediate function u, and you're trying to find dy dx, if you can find the derivative of y with respect to u, and then you can find the derivative of u with respect to x, the product of those derivatives is the derivative of y with respect to x. Now the extra step that has to be gone to is if you have the derivative of y with respect to u, probably that has u's in it. But u has been expressed as a function of x, so you take any place where you see a u and replace that with the expression that has x's in it. In this case, we've got derivative of f of some expression u. Since y equals f of u, dy dx, let me write it directly underneath there, dy dx equals f prime, not of x, sorry, f prime of u. So what I've done is I've picked up the dy du and replaced it with f prime of u. Oftentimes it's simpler to think of it in that regard. So example 2, it wants us to find dy dx, and we have y equals an expression raised to the third power. So the outside function is what we're calling f. We're taking the derivative of something raised to the third power. Now we could take the time to write it down if we want to. F of x equals u cubed, but usually we won't. We'll just realize we're taking the derivative of the cubing function composed with 3x squared plus 4x plus 5. Since it's the first one of today, I feel like it would be good if I would be as deliberate with this as possible. So let me throw in the extra variable, and then again quickly without the extra variable. If we're going to throw in the u, what we would say is that u equals 3x squared plus 4x plus 5, the inside function. That's u. We did one similar to this last time. It might have been the same example, or one just different by a number or two. Very, very similar example. And also then y equals u cubed. But that's a good feeling in a math class when you're sitting there thinking, I've seen this somewhere before. Even if it was just the previous class period. That's a good feeling rather than, I've never seen anything like this before in my life. How am I going to do this? Du dx equals 6x plus 4. We take that derivative. And dy du equals 3u squared. We take that derivative. And then according to this up here, we multiply dy du by du dx. So dy dx equals dy du times du dx. That's going to be 3u squared times 6x plus 4. And then it has a u in it. We were expecting it to have a u in it. So we substitute 3x squared plus 4x plus 5 for that u. So this is 3 times 3x squared plus 4x plus 5, quantity squared, times 6x plus 4. Other than factoring a 2, maybe out of the 6x plus 4, that's the final answer. So in looking at this, what we observed last time, right at the end of class, was that if we wanted to take the derivative of 3x squared plus 4x plus 5, quantity to the third power, then you could think of it as using the power rule. It's kind of a generalized power rule, but you could think of it as using the power rule. You'd take the 3, bring it out in front, and there it is right there. You'd reduce the exponent by 1 from a 3 to a 2, and there it is right there. And so you would have 3 times whatever's inside the parentheses raised to the second power. Now the thing we have to keep in mind is, and I'm saying it for the second or third time now, I'm going to say it probably 20 or 30 times more, the chain rule says multiply by the derivative of what's inside the parentheses, the inside function. We have to multiply by the du dx. So we multiply by 6x plus 4, and that gives us the answer. Now, using the generalized derivative formula, when we look at this, here's the way we want to think of it. Y equals an expression raised to the third power. Well, the derivative of an expression raised to a third power is 3 times that expression raised to the second power times the derivative of that expression. That's the way we want to think of it when we're evaluating the chain rule. Just how do we take the derivative of something raised to the third power? Well, bring 3 out in front, reduce the exponent by 1, and then multiply by the derivative of that expression. Let's try this one. Y does not equal the derivative of this. We're not finding the second derivative here, so this is a misprint. Sorry about that. Y is just that expression. So Y equals x to the 5th plus 10x quantity to the 1/2. So we look at it and we ask ourselves, how do we take the derivative of something raised to the 1/2 power? Well, it's the power rule. It's 1/2 times that expression raised to the negative 1/2. We subtract 1 from the 1/2 times the derivative of that expression. So dy dx, without a lot of fanfare, equals 1/2 times x to the 5th plus 10x to the negative 1/2 times (5x to the 4th plus 10). Like that. We multiply by the derivative of what's inside the parentheses, and that's the derivative of what's inside the parentheses. And yes, probably I should write this in a little bit nicer form, factoring out the 5, and also, since it was given in terms of radical, maybe if I can write my final answer in terms of radical. So let me try to clean this up a little more than I did the previous example. Dy dx equals, let's see, 5 times x to the 4th plus 2 over 2, the 1/2 out in front, we could express that as having a factor of 2 in the denominator. So 2 times, now if I take the negative exponent, negative 1/2, and shove that expression down to the denominator, I'll have the positive 1/2. So it's going to be the square root of x to the 5th plus 10x. Possibly, I guess you could factor an x out of that little expression there. There's really not another x to any power in the expression as a whole, so I don't know that I see the real virtue of doing that, but that's something that you could do if you wanted to. Does this look okay? So the derivative of an expression composed with another, the outer function is what we want to think of. Well, how would we take the derivative? What's the rule for taking the derivative of the outer function? Goodness, we did those trig functions. I think we're going to need to review this. Maybe up here would be good. How about d dx of just plain old secant x? Secant x tangent x. That's what it was, right? So the derivative of plain old secant x is secant x tangent x. Now, applying the generalized derivative formula to this, if we want to find the derivative of secant u with respect to x, now we have to imagine u could be any expression with x's in it. It might be x cubed. Right? U could equal x cubed. It could be an expression with x's in it. How would we go about this? Well, the derivative, in this case, secant is the outside function. So what we would say is it would be secant u tangent u times the derivative of u with respect to x. Put a dot there. I don't know if a dot with or without the dot is the indication of multiplication. Chain rule says multiply by the derivative of what's inside the parentheses, and although the parentheses aren't all that prominent, there are implied parentheses around the u there. So we have to multiply by the derivative of u. So the derivative of the secant of something is secant of that something times tangent of that something times the derivative of that something. That's how we do that. So this is going to be secant of x cubed times the tangent of x cubed times the derivative of x cubed. Well, easy enough, 3x squared, right? So secant x cubed tangent x cubed times 3x squared, and probably the 3x squared should go in front. Just so there's no confusion, we're taking the tangent of what? We're taking the tangent of just x cubed. If I shove the 3x squared up next to that, that could confuse things. So 3x squared secant x cubed tangent x cubed. If we didn't have the chain rule to tell us what to do, probably would have left off the 3x squared. But chain rule says multiply by the derivative of that u there. Now, example 5. I'd probably be well advised to write this not using the special notation we use for exponents with trig functions, but rather to write it like this: d dx of secant x cubed. So I haven't taken any derivatives yet, but that's what we mean when we say secant cubed x. We mean take the secant of x and then cube that. That's what that notation means. So if I write it like that, maybe it's a little bit easier to see that the outside function is not the secant function. The outside function is the what? The cubing function, yes. So how do we take the derivative of something cubed? Well, power rule. 3 times that something raised to the second power times the derivative of that something. It's a role reversal. Basically, it's composition of functions, but I'm reversing the order of the composition. Rather than cubing first and then taking the secant, I'm taking the secant first and then cubing. And so the outer function is now the cubing function. Well, now it's just a matter of copying and pasting and using some notation. 3 secant squared x, because that's what that means. Secant x quantity squared is secant squared x. That's how we write it. And now the derivative of secant x, copy and paste this from up here, secant x tangent x. Oh, I guess there's one more step on to clean things up. Secant squared x times secant x, secant cubed x. So 3 secant cubed x tangent x. Starting point by thinking, what's the outside function, the outermost function in the composition, and then we multiply by the derivative of what's on the inside. Examples 4 and 5 and the preceding examples could be thought of the chain rule with a single link in the chain. Examples 6 and 7, we've got the chain rule with maybe a couple links in the chain. When you studied composition of functions, you know that, well, let's see how to do this. I'm trying to think of what would be f composed with g composed with h of x is equal to f of g of h of x. So there's something kind of like that going on with these next two examples. And we just need to figure out what is the outermost outermost function, and start by taking the derivative of that. And as we multiply by the derivative of what's inside the parentheses, the expression that's inside the parentheses will also be written as the composition of multiple expressions. So let's see, if I'm going to evaluate this, if I'm working from the inside out, the first thing I would do is evaluate this polynomial, x squared plus 5x plus 3. That's the innermost function, x squared plus 5x plus 3. After that, so that's, I guess, the h of x. H of x equals x squared plus 5x plus 3. And then the g of x, the next thing I would do is take that and do what with it? Cube it. So I would say g of x equals x cubed. That's the next to the innermost function. That's the one in the middle. And then after I cube that, one more thing left to do. Take the sign. So this function could be thought of as the composition of these three functions in that order, from inside to out. Now the outermost function is the sign. That's the last thing you do if you're going to evaluate this function. Take the sign. So when I look at this, I should think, okay, I want to take the derivative of the sine of something. Well, the derivative of the sine of something is what? The cosine of that something. So all the something there, the cosine of that something, all of that, times the derivative of that something. So the derivative of the sine of that expression is equal to the cosine of that expression times the derivative of that expression. So we write that down. Don't have to do much more with cosine. Maybe write cosine cubed instead of, well, let's see, no, I'm not cubing the cosine. I'm keeping the expression inside, so check that. Copy and paste that down below. Cosine of x squared plus 5x plus 3, that quantity cubed. Now, it's the derivative of something cubed. So we use power rule, bring that 3 out in front. The derivative of something cubed is 3 times that something raised to the second power, reducing the exponent by 1, times the derivative of that something. So 3 times that something to the second power times the derivative of that something. And then we're almost there. Just one more easy derivative to take. Chain rule has been pretty much exhausted there, and we just need to use the power and sum and difference rules from that point on. So it's going to be, how to clean this up, the 3 times the expression to the second power, probably should go in front, then the cosine. Well, it's going to be a little bit more to it, I guess, when I take that derivative. Let me just not do too much there. More copying and pasting. The cosine of x squared plus 5x plus 3 quantity cubed times 3 times x squared plus 5x plus 3 quantity squared times 2x plus 5, derivative of that polynomial, 2x plus 5. And now, not a lot of rearranging to do. The 3 should go in front, and then those two polynomials, either the 2x plus 5 or the x squared plus 5x plus 3 quantity squared, should come next. And then the cosine probably last. Not a huge deal. If you left your final answer like this, I would not count off for it. So 3. You think it would look nicer with the 2x plus 5 next or the x squared plus 5x plus 3 quantity squared next? You want to have a preference there? No preference? Okay. I'm going to go with the 2x plus 5 next. For some reason, that just feels right. X squared plus 5x plus 3 quantity squared cosine of x squared plus 5x plus 3 quantity cubed. There. So chain rule with an extra link in the chain, basically, is what's going on there. And I give that example and contrast it with this next one, because it's the same 3 functions, except the innermost function here, the innermost function is, well, the same, huh? H of x. Is it the same? the first thing I would do is evaluate x squared plus 5x plus 3. I think it is. And then the other two functions reverse roles. The next thing I would do is what? Take the sine. Yeah, so sine x is next. And then the last thing to do after you take the sine, cube it. So the sine function and the cube function, I suppose I could have permuted them in a more interesting way, those three functions there, but that's okay. I swapped the last two.
So how do we know that sine of x comes before the x cubed?
Oh, great question. Let's see. Just imagine plugging in a number. Maybe you're trying to evaluate it x equals 0. Let's just keep it simple. You plug in 0 for x, and the first thing you do is say 0 squared plus 5 times 0 plus 3, and you get 3. And then you're thinking, okay, what do I do with that 3? So it's sine, basically sine cubed of 3 in that case. So you would ask yourself, would you take that 3 and cube it and then take the sine? Or would you take the 3 and take the sine and then cube that? It's 3 radians, basically. Or I guess it could be 3 radians. Since this means the same thing as the sine of 3 quantity cubed, the next thing you do with that 3 is take the sine. So sine is the middle function. The very last thing that you do in this case is cube it. That's the last thing to do. So the outermost function is the cubing function. It would help to see that if I would rewrite this as ddx of the sine of x squared plus 5x plus 3. One more set of parentheses. Squared. I hesitate to put the squared without an extra set of parentheses because then we'll wonder, x squared plus 5x plus 3, are we squaring that and then taking the sine, or is it cubed? Oh, thank you. Yep. That should be a cube. Thank you. So are we cubing that and then taking the sine? Or are we taking the sine and then cubing this? With the parentheses placed like they are, we're taking the sine first.
Yeah, that helps.
Taking the sine first. And then finally we're cubing. I guess taking the sine after we evaluate that expression, of course. So, clean up some of the mess. So when I look at this and I get ready to begin, derivative of the outermost function is the cubing function. So the derivative of something cubed is 3 times that something raised to the second power times the derivative of that something. 3 times that something raised to the second power, just applying the power rule to that. Taking the 3 out in front, reducing the exponent to 2, and then knowing not to leave it like that because the chain rule says I've got to multiply by the derivative of what's inside the parentheses, and so I'm going to multiply by the derivative of the sine of x squared plus 5x plus 3. So now, derivative of the sine of something. What did we say last time? Last example, derivative of sine of something is the cosine of that something. And according to the chain rule, times the derivative of that something. So copy the 3 times sine. At this point, I actually can get by with calling this sine squared. The notation is appropriate there because we're actually squaring the sine of that expression. So 3 times sine squared of x squared plus 5x plus 3. Now I'll take the derivative. Derivative of the sine of that expression is the cosine of that expression. Cosine of x squared plus 5x plus 3 times the derivative of x squared plus 5x plus 3. You know what the most common mistake is I see on tests with the chain rule? Students know they've got to use cosine, and they know it's got to involve the derivative, 2x plus 5? So what do I see? I see the cosine of 2x plus 5. And it makes me so sad to see that, because it just you're thinking the right things, you know, it all has to happen, but it doesn't happen. You don't compose the cosine with the derivative. It's the cosine of the original expression, and then you multiply by the derivative of the original expression separately. So they just kind of get jumbled together. But if you do, you know, a couple pages of these, then it'll be clear in your mind what to do there. I don't know if I've given you a couple pages of them. Maybe I've just given you a half a page of them. So I should probably give you more. 3 sine squared of x squared plus 5x plus 3. Cosine of x squared plus 5x plus 3. And then times 2x plus 5. Maybe make it like that. Is it maybe a little bit ambiguous? Maybe grab the 2x plus 5 and bring it out in front. That's the only thing I might suggest. Otherwise, you could leave it like that. So 3 times 2x plus 5 times sine squared of x squared plus 5x plus 3 times cosine of x squared plus 5x plus 3. And that's got to be enough, huh? Chain rule is designed, like all these rules, product rule, quotient rule, to make our lives easier. Does your life feel easier now than it was when you came in here today? No? That was the idea. Might have missed the mark just a little bit. Maybe if I'd given you examples 8 and 9 and said, find the derivative of each of these using something other than the chain rule, that might have given you a little bit better appreciation for the chain rule. Let's see. It stands right here. What we've got is a couple of functions, I think each of which we can handle individually. X squared. We won't have any trouble finding the derivative of x squared, right? No trouble there. The other one is the square root of 1 minus x squared. Now the inside function, 1 minus x squared, we can find the derivative of that. It's a polynomial. And the square root function, because that's x to the 1/2. We can find the derivative of that. So what we have is a product. So I hope you're thinking product rule. Product rule. I'm going to use the product rule to find the derivative of this product. We'll refresh our memories as what the product rule is all about. We haven't had that on a test yet. And then when we get at some point in the product rule, how does that go, by the way? Derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. That's how that goes. So at some point along the way, early on actually, we have to calculate the derivative of that second function. When it comes time to find the derivative of the square root of 1 minus x squared, that's when we'll have to use the chain rule. So the basic framework of this is the product rule. But because we have the chain rule, that enables us to take the derivative of the square root of 1 minus x squared, and we'll be able to plug that in at the appropriate time. So we're going to think of this as a product, and the second factor, when we have to take its derivative, we'll use the chain rule to calculate its derivative. So here goes. Product rule. Product rule. F prime of x equals the first times the derivative of the second. Now, I'm going to go ahead and write it as 1 minus x squared quantity to the 1/2. I'm not taking a derivative. I'm just rewriting it in a friendlier form so that when we get to the point where we take the derivative, it's easier using fractional exponents than it is dealing with the radical. So the first times the derivative of the second plus the second, 1 minus x squared to the 1/2, times the derivative of the first. That's the product rule. Basic framework for the derivative of this function. Now, derivative of x squared will be no problem. That's just 2x. But the derivative of 1 minus x squared to the 1/2 will involve the chain rule. It's the derivative of something raised to the 1/2 power. So if we're looking at that, thinking, what's the outermost function? The last thing we would do when evaluating that, the very last thing we would do, if we're punching that up on our calculator, is take the square root. If you want to plug in 0 for x, evaluate that at x equals 0, you would square the 0, you would subtract it from 1, and then finally you would take the square root. So that's the outermost function in that in evaluating that expression. So f prime of x equals x squared times the derivative of something raised to the 1/2 power. Here we go, chain rule. Derivative of something raised to the 1/2 power is 1/2 times that something to the negative 1/2 times what else? Put that yes, times the derivative of that something, which in this case is 1 minus x squared. So it's like we're just applying the power rule. 1/2 comes out in front. We subtract 1 from the exponent. We get negative 1/2. We keep the expression inside the parentheses the same, and then we multiply by the derivative of the expression inside the parentheses. Eventually, the next step, that'll be what? Negative 2x that we get down there for that. Plus 1 minus x squared to the 1/2 times 2x. Easy one there. No chain rule necessary. All right. It's about to get a little algebraically ugly. And I apologize for that, but the idea is a clean, neat final answer. But a little bit on the, a little bit of ugly algebra here. Got to take a derivative. Going to leave it in the negative exponent there. Maybe take the 1/2 out in front. 1/2 x squared times 1 minus x squared to the negative 1/2 times negative 2x. That's really all the excitement that's happening to that expression right there. Take the derivative of 1 minus x squared, you get negative 2x, plus maybe the 2x out in front of that expression, 1 minus x squared to the 1/2. I'd like to say, what's another obvious thing we could do here before I'd say what I'd like to say? Something that we're simplifying. We're definitely going to factor. I'm thinking the 1/2 and the negative 2. Something easy. What's 1/2 times negative 2? Negative 1. The 2's basically scratch each other out, divide each other out. So that'll be the negative 1 there. And also x squared times x. Looks like we get x cubed. So minus x cubed to leave that expression. Let me go ahead and do that much, and then I'll tell you what I'd like to tell you. Negative x cubed times 1 minus x squared to the negative 1/2 plus 2x times 1 minus x squared to the positive 1/2.
Can you say again where the x cubed came from?
Yeah, I lost it.
Well, the x squared here times the x here on the end. I think we can multiply those together. That's x to the 1 and that's x to the 2. So add the exponents there, we get x to the 3rd power. X squared times x equals x cubed. Yeah. So we've long since taken the necessary derivatives. This is the derivative. These last two steps represent the derivative. I haven't made a mistake somewhere. I don't think I have. Let me know if I do. But a nicer way to write this would be factored form. Eventually, in the not too distant future, the next chapter, we're going to be interested in zeros of the first derivative. Values of x that make the first derivative equal to 0 give us horizontal asymptotes, places where a function may stop increasing and start decreasing, or stop decreasing and start increasing. Horizontal asymptotes aren't the only place where that happens, but it's a common place where it happens. So it's a common thing to take the derivative, set it equal to 0, and solve for x. It's a lot easier to deal with an expression set equal to 0 in an equation if it's in factored form, rather than right now it's the sum of two expressions. So I want to factor out a common factor. Now I see the x cubed and the x, so certainly x is going to be a common factor that we can factor out. But also we've got a 1 minus x squared to a power in each one. Now as a rule, when you're factoring out, suppose I have 4x plus 5x squared plus 7x cubed. Good enough, I guess. I would like for it to be more interesting than that. X to the fifth power. How about that? Does that look like a 5? No, it doesn't. It looks like an upside down 2. There we go. 4x to the fifth plus 5x squared plus 7x cubed. If you're factoring out the greatest common factor, it's going to be x to the what? X to the second. The rule we use is go with the least of the exponents, because x raised to the least of those exponents is going to be a factor of all of them. If we go with the greater exponent, it won't be a factor. So we go with the least of those exponents. So here's the thing. 1 minus x squared is raised to the negative 1/2 there. 1 minus x squared is raised to the positive 1/2 there. Got a negative 1/2 and a positive 1/2. We want to go with the lesser of those two exponents. What's less, negative 1/2 or positive 1/2? Negative 1/2 is less. So GCF looks like this. F prime of x equals x times 1 minus x squared to the negative 1/2. You have a common factor of x, and they each have a factor of 1 minus x squared to some power, and the lesser of those two powers is negative 1/2. So we're going to go with the lesser of those two powers as our exponent. And now, one at a time, we look at each of these expressions and ask ourselves, x times 1 minus x squared quantity to the negative 1/2 times what will give us that expression? I bet we need a negative sign. We need an x squared.
Plus 2.
And
Plus 2 to...
plus, yeah, we're going to need a 2 there. Times 1 minus x squared to what power? So that if I add negative 1/2 to that power, I get positive 1/2. Negative 1/2 plus what will give me positive 1/2? 1.
Do we have to write the 1 or not?
As long as you know that it's there, you don't have to write it. So I'm going to erase it, because I know it's there. There. So 1 minus x squared. And then simplify what's inside the parentheses. By our choice of the exponents, because we went with the lesser of the two exponents on the x's and the lesser of the two exponents on the 1 minus x squareds, we get a nice polynomial on the inside. So we can simplify that, and let's see if we can. F prime of x equals, oh, wow, let's see. The x is on the outside. So I want to write x times, I'll stick with the brackets, I want the square root of 1 minus x squared in the denominator. Why in the denominator? Negative 1/2 is the exponent. So I shove it down to the denominator, make it positive 1/2, replace the exponent of positive 1/2 with a radical. And then if I can just combine like terms, negative x squared minus 2x squared. You see a negative 3x squared there? And then plus 2. How do you feel about this? That seem all right?
Well, the numerator or the last step again, please?
The negative 3x squared? Negative 3x squared, what I'm doing is I'm taking this expression, because I'm short on space, I'm writing it negative x squared plus 2 minus 2x squared, and then combining those two to get negative 3x squared, and then plus 2. I was just short on space there. Yes.
One step above that.
One step above that, I think is kind of a rough one as well. Well, basically, we did it kind of quickly, maybe more quickly than I'd hoped, but we're looking at this expression right here, and we're asking ourselves x times 1 minus x squared to the negative 1/2 times what, and the what is going to go in the orange here, times what will equal that. So I see a 2 there, so I knew I need a 2. I've already got an x, so I don't need another x. And I've got a 1 minus x squared to the 1/2. And so I'm wondering 1 minus x squared to the negative 1/2 times what equals 1 minus x squared to the positive 1/2. And if I multiply by 1 minus x squared to the positive 1, that will get me from negative 1/2 to positive 1/2. So that would be the final answer. And I probably need to indicate, write your final answer so that it's in factored form rather than the sum of two expressions, just to let you know not to stop, because we found the derivative up here. We've got the derivative. You know, chain rule, suffered through the chain rule, done that, but it's a lot of algebra from there to the end. Let's see if example 9 is any better. I suspect it might actually be a little worse. Because it involves not the product rule, but what? Quotient rule. So that's the framework. We know we can take the derivative of x, and if we have the chain rule at our disposal, we can also take the derivative of the cube root of x squared plus 4. That's a composition of two functions, each of whose derivatives we know how to find. So this is the quotient then of two functions whose derivatives we know how to find, and the quotient rule goes like this. F prime of x equals, take whatever's in the denominator, put it in the denominator, and square it. So what's in the denominator is x squared plus 4 to the 1/3. What do we get when we square x squared plus 4 to the 1/3? I suppose there's plenty of time to figure that out. You get that? While we're thinking about it, take that expression, x squared plus 4 quantity to the 1/3, and write it down right up here. X squared plus 4 to the 1/3. I didn't take the derivative of that, so it must be that we need to take the derivative of the numerator. So multiply by the derivative of x. No trouble there. And then it's a minus. Quotient rule is a minus, so it's why it's important to have the order of those two quantities in the numerator correct. So the first quantity, the one that I've written, is the denominator times the derivative of the numerator. And then we subtract the numerator times the derivative of the denominator. That's the framework. That's the quotient rule. So we take the necessary derivatives. F prime of x equals, okay, the derivative of x is 1. I could write the 1 or just kind of notice that it vanishes since we're multiplying by 1. Should I write the 1? It won't hurt to write the 1. X squared plus 4 to the 1/3 times 1 minus x times, okay, chain rule time. I want to take the derivative of x squared plus 4 quantity to the 1/3. So it's thinking the outermost function. Outermost function is the cube root function, the raising to the 1/3 function. So the derivative of something raised to the 1/3 power is 1/3 times that something to the, what's 1/3 minus 1? Negative 2/3 times the derivative of, and here's where I'm going to play fast and loose with the notation. I'm not going to write, I probably should write d dx of x squared plus 4, yes? Yes, I should. When you go back and look at this, you'll think, where did the 2x come from? Oh my goodness, he's just making stuff up. And I might be, but at least I need to leave good directions as to where it came from. d dx of what's inside the parentheses. So multiply by the derivative of what's inside the parentheses because the chain rule said so. X squared plus 4 to the 2/3. Multiply those exponents and that's what we get. 1/3 times 2 equals 2/3. So we'll take the derivative of x squared plus 4 and get 2x. Maybe there's some other things that we can do. Is it too soon to think about factoring a common factor out of the numerator? X squared plus 4 to some power? F prime of x equals... It's not too soon to start thinking about it. It feels like it's too soon to start doing it. X squared plus 4 to the 1/3 minus 1/3 x times x squared plus 4 to the negative 2/3 times 2x over x squared plus 4 to the 2/3. So not a whole lot of excitement there. Derivative of x squared plus 4 is certainly 2x, and the x and the 1/3 just kind of swap places because I like the coefficient out in front of the expression if possible. A little bit more that has to happen there. Goodness. Copy and paste all of that, and what's going to happen? The 2 is going to find itself in the numerator of that fraction, call that 2/3, and instead of an x there and an x way over there, I'll just have an x squared. That's all that's really going to happen there. So here goes. Don't want to erase that. F prime of x equals x squared plus 4 to the 1/3 minus 2/3 x squared times x squared plus 4 to the negative 2/3 all over x squared plus 4 to the 2/3. Okay, now it's time to factor x squared plus 4 to some power out of the numerator, and once we do that, we'll be able to get that together with the x squared plus 4 to the 2/3 down in the denominator. But let's first deal with the numerator. We've got a power of 1/3. We've got a power of negative 2/3. What is the lesser of those two powers? Negative 2/3. So I'm looking at it, I'm thinking I don't want a 2/3 inside the parentheses. I don't want to leave a fraction inside the parentheses like this. So I'm wondering if I shouldn't, at a minimum, factor out a 1/3. It's a little weird, but I want to think factor out a 1/3 times x squared plus 4 to the negative 2/3. And then we'll have an x squared plus 4 to the positive 2/3 down there. If I don't factor out that 1/3, then I'll factor out what I have, and then inside the parentheses there'll be a polynomial with the fractional coefficient. And I don't want any polynomials with fractional coefficients inside. I just want integer coefficients, if I can keep it that way. So that's why I'm just trying to look ahead and deal with that 1/3 proactively. So we look at it and we ask ourselves, well, let's just ask ourselves this. 1/3 times what equals 1? Can we answer that question? 1/3 of what equals 1? 3. We're going to need a coefficient of 3 for this first expression here. I need a 3 there because I factored out the 1/3 when the first coefficient wasn't really divisible by 3. So I factored out the 1/3, and then x squared plus 4 negative 2/3 plus what equals positive 1/3? 1. So again, we don't have to write the 1. We just have to know that there's a 1 there, an invisible 1, if you like. Minus 1/3 times 2 will give us the 2/3. And I guess that's enough, huh? Kind of anticlimactic for the numerator there, but that's really... Oh, no, we need the x squared, don't we? Yeah, I almost overlooked the x squared. Sorry about that. Didn't mean to scare anybody. It scared me. Hopefully no one else. X squared. All right, is that good? Maybe not the final answer, but so far so good?
Sure.
Yes. All right. So let's do two things. let's get the x squared plus 4 to the negative 2/3 and the x squared plus 4 to the positive 2/3 together somehow. We like positive exponents. So if we take that x squared plus 4 to the negative 2/3 and shove it down to the denominator, it'll look like this. Why don't we take the 1/3? That's like 3 to the negative 1. Shove it down to the denominator, we get 3 to the positive 1. All right, x squared plus 4 to the positive 2/3. Another x squared plus 4 to the positive 2/3. And then let's deal with what's inside the brackets there in the numerator. If we deal with that, distribute the 3 across the parentheses, since that's just a 1 there. I'm going to leave it visible. 3x squared plus 12 minus 2x squared. Are we in a position to write the final answer? Is it about time? F prime of x equals x squared plus 12 over 3 times x squared plus 4. Add those exponents. 2/3 plus 2/3 equals 4/3. And the final answer looks like this. Comparatively nice, I think, compared to how it looked in the middle. In the middle, it was really rough. A moderately elegant looking final answer. Let's look at the derivative of the natural log function. In college algebra, we studied the exponential function, y equals e to the x. And we'll study here as well. Y equals e to the x, basically e to the 0 power equals 1, and e to the first power equals e. 2.7 something, 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 something. So that's a 0.1 e. And then the reciprocal of e is a little bit less than 1/2. So that's e to the negative 1. So the graph of y equals e to the x looks something like that. The inverse function, if you take that graph and reflect it about the line y equals x, you get the graph of the inverse function, and it has 1, 0 on it. And E1 is right there. And let's see, if I have negative 1 over e, I have 1 over e negative 1. So one has a horizontal asymptote, one has a vertical asymptote. This is the graph of y equals the natural log of x. So what we wanted to establish is the derivative of the natural log of x is 1 over x. That is, if I got a point on the graph, that's the point E1 right there. Then the slope of the tangent line to the graph would be 1 over e. That's what they're saying. As we go to the right here, then it gets less and less steep, just like 1 over x, as x increases, approaches 0. So it approaches, having a horizontal tangent line just never quite gets there. That's what we want to establish for positive values of x. Of course, with the log function, we can't take the log of 0, and we don't generally take logs of negative numbers. We get imaginary numbers when that happens. So to do that, we want to take the log of a more general function, log base b of x. Log base b of x, and in doing so, then if we substitute e for b, then we'll be able to write the derivative of the natural log function because the base is e, the natural base there. So using the definition of derivative, instead of delta x, I'm just going to use h. Some textbooks do that. Rather than defining the derivative in terms of the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0, they use h to represent a small non-zero number that's approaching 0. So I'm going to do that rather than delta x. I suppose if I wanted to redo it, I could use delta x, but since it's already done, I'm going to leave it like that. So we're going to take this as the definition of the derivative. We're evaluating the log at x plus h, and then we're letting h approach 0 with h in the denominator there. What happens next is that we use a property of logarithms. The difference of the logs equals the log of the quotient. So we're taking the difference of the logs here. The x plus h goes over the x, so it's log base b of x plus h over x. That's just a property of logarithms that we try to wear that one out in college algebra and pre-calculus, and hopefully we do an adequate job there. Then dividing by h is equivalent to multiplying by 1 over h. So the 1 over h basically gets factored out in front of that. And the expression x plus h over x is going to be easier to handle if we write it x over x plus h over x, and then x over x, of course, is 1. So we get 1 plus h over x. So we're taking the log of that expression, log of 1 plus h over x, and h is still approaching 0, so we can't apply direct substitution until we can deal with that h in the denominator. Here's where we do kind of maybe an unexpected substitution. It works out nicely though. We let v equal x over h. What we want is an expression. We're eventually going to use this fact when we study compound interest in college algebra and in pre-calculus. We talk about the number e, and we say that the expression 1 plus 1 over, usually we use n or m instead of v here, but as the letter v approaches infinity, 1 plus 1 over v to the v, actually the value of that limit is e. And although we don't necessarily take that as a definition of e, it can certainly be used to give an approximation for the number e. So using this substitution, we would have to answer the question, as h approaches 0, where does v go? Well, I suppose we have to clarify, is h approaching from h approaching 0 from the right, or is h approaching 0 from the left? Well, I'm going to say h is approaching 0 from the right, and we could do a separate case and consider what happens if h approaches 0 from the left. But in the special case, h approaches 0 from the right, v is going to positive infinity, because x is just hanging around at x, and x is positive. So positive x divided by a tiny positive h is driving the value toward positive infinity. So it's approaching positive infinity. So we carry out the substitution. It's a little bit better if I'm writing this out probably rather than just pointing at it. But if v equals h over x, then 1 over v equals h over x. So we pick up the h over x and put a 1 over v in its place. And the 1 over h, that's a little bit tough to see there. But let's see, suppose vh equals x. How do I get the h in the denominator? V equals x over h. V over x equals 1 over h. Sure, that works. So that gives us the v over x there. Keep in mind that x is not approaching anything. X is just hanging around at x, because this is to be a function of x. So x stays right there, and I'm going to separate the 1 over x and the v over 1. So we look at this expression, and we let v approach infinity. V is approaching infinity. Now, it's kind of a key thing that we do here. I want to pass the limit, let's see, I want to pass the log through the limit right here, because the log function, based on our experience with it, well, there's the picture, it's a continuous function. And kind of like we did with limit of f of g of x, we pass the f through the limit. We can pass the log through the limit for that reason because it's continuous. And then we have the log of the limit of that expression, but that expression is equal to e. So we evaluate the limit like that, and it's 1 over x times log base b of e. Using the change of base formula, you can write that as the natural log of e divided by the natural log of b, and the natural log of e equals 1. So, no, I'm not going to ask you to derive that on the test. What a pain that would be. But you do need to memorize a couple of derivatives here. Derivative of log base b of x is 1 over x times the natural log of b. And if you substitute e for b, natural log of e is 1. So the derivative of the natural log of x is simply 1 over x. So we will take that as a reasonably well-derived derivative limit. d dx of natural log of x is 1 over x. You can look back at that, and if it didn't make much sense this time, well, perhaps it will a little bit more in the future. Keep these limit definitions in mind together with the chain rule. Let's see if we can take these derivatives. Derivative of log base 5 of x. Well, this is a straightforward example of this one right here. Let's go back to blue. That red is troublesome. d dx of log base b of x, 1 over x. You just have to have a factor of natural log of 5 in the denominator. So this is 1 over x natural log of 5. A little neater with that. There we go. 1 over x times the natural log of 5.
What's the answer?
That is the final answer for the A part, just to get us warmed up. As if we're not already warm enough at a minute till 2 here. d dx of log base 3 of this expression, this is the chain rule. Whoa, from warmed up to revved up. The derivative of the outside function is the log. So we have to think, okay, the derivative of log base 3, like we've done almost one of those in the course of our lifetime. Derivative of log base 3 is going to be 1 over, let me say it one more time. The derivative of log base 3 of an expression is 1 over that expression times the natural log of 3 times what? The derivative of that expression. d dx of x to the 4th minus 4x squared plus 5. So it's going to be 4x cubed minus 8x. Factor out the x if you like to. Factor out the 4x if you like to. Over x to the 4th minus 4x squared plus 5 times the natural log of 3. And the C part, we're going to be using, well, actually, this one officially. d dx of the natural log of u is going to be 1 over that expression u times the derivative of that expression. So this is going to be 1 over the sine of u, sine of x, sorry. Sine of x is the expression u. 1 over the expression times the derivative of that expression. And we'll see this time and again. 1 over that expression times the derivative of that expression. What's the derivative of sine x? Cosine x. So this is going to be cosine x over sine x. And this is cotangent x. Now what we've seen in the course of taking derivatives is we've seen the derivatives of the 6 trigonometric functions. And we almost have all 6 of them memorized, yes? Yes, all 6 trig functions. At some point, we'll start considering antiderivatives. And we'll ask ourselves, what can I take the derivative of to get a particular function as the answer? And at some point, it'll be, okay, what can I take the derivative of to get cotangent x? When we get there, we ask ourselves this question, we'll have no memory at all of having done this example. It will be as far from our consciousness as imaginable. But the answer would be, well, of course, natural log of sine x. That's what you would take the derivative of to get cotangent x as the answer. So maybe we can think back to this example when we get there and ask that question. Example 11. This would be as horrible, no, actually 2 or 3 times as horrible as examples 8 and 9 that we did previously. If you could just kind of imagine this, we've got the natural log function composed with this hideous expression where there's a product in the numerator, and we've got basically the natural log of a quotient. The chain rule would come into play for the derivative of the cube root of x squared plus 5, also for tangent cubed x. So we'd have the chain rule, and inside of that we would have the quotient rule, and inside of that we'd have the product rule in the numerator and the chain rule in the denominator, and inside of the product rule we would have the chain rule. So it's like several degrees of what was the movie? Inception? Yes. It's like, oh gosh. Anyway, it's way better than that. We exploit the properties of the logarithm to make the expression that we have to differentiate as simple as possible. And then it's much easier than that. So no derivatives. Natural log of a quotient equals the difference of the logs. So y equals the natural log of x to the 5th times x squared plus 5 to the 1/3 minus the natural log of tangent x cubed. So, no derivatives, just log of a quotient equals the difference of the logs. And then we have the log of a product. So we say log of the product equals the, not x, equals the sum of the logs, the natural log of x to the 5th plus the natural log of x squared plus 5 to the 1/3. And we could go ahead and do this here. Natural log of an expression raised to a power. What happens to the power? And it goes in front, so 3 natural log of tangent x, like that. And then also the 5 comes out in front, so y equals 5 times the natural log of x plus 1/3 times the natural log of x squared plus 5 minus 3 times the natural log of the tangent of x. At that point, we can think about taking a derivative, because it still involves the chain rule. The log is composed with another function in each case, but there's no quotient rule, there's no product rule, and there's no rule inside of a rule inside of a rule. So dy dx time, there we go, dy dx. This is just the constant multiple rule. Derivative of 5 times natural log of x is 5 times the derivative of the natural log of x, so 5 times 1 over x. Nothing fancy going on there at all. A little fancy for the next one. It's 1/3 times derivative of natural log of an expression is 1 over that expression. Maybe I shouldn't make the division bar that long. 1 over that expression times the derivative of that expression minus 3 times derivative of the natural log of an expression is 1 over that expression, 1 over tangent x times the derivative of tangent x. The remaining derivatives, I think, goodness, I might need a little bit more space, but nothing really difficult left. 5 over x plus Could we say 2x over 3 times the quantity x squared plus 5? The derivative of x squared plus 5 is 2x. And then minus 3. I really would like the 3 to be a factor of the numerator. 3 times something with tangent x in the denominator. What's the derivative of tangent x? Secant squared x. And there are certainly alternate ways to write secant squared x over tangent x. I don't know if there's one that's obviously better, shorter, sweeter, clearer than secant squared x over tangent x. You might have a nice...
It's supposed to be another parentheses down on the bottom there. 3
In the
x
middle,
squared
2x
plus...
over 3x.
This one right here? Yes, definitely, yes. I think that's it. I think that's it. So, to see what... Oh, was it? There it is. Give it a minute, and then one more minute to see what we... what else? I guess I need to take stock. I'll go ahead and upload this.